Welcome to one more lecture on subRiemannian geometry. I previously mentioned how Carnot groups and subRiemannian manifolds appear as limit spaces. I will now comment on the reason. I'm going to state a fact that I will later motivate to explain what happens to distances coming from sequences of Carnot-Carathéodory structures that converge. So let's talk about limits of Carnot-Carathéodory structures. I claim that both Mitchell's theorem on tangent spaces, tangents of Carnot-Carathéodory spaces, and Pansu's theorem on asymptotic spaces, asymptotic cones of nilpotent groups. These are two theorems that we mentioned in the previous video. Nilpotent groups are based on the following more general fact. Namely, I want to see these two theorems as a consequence of this following theorem. Of course, one should then really verify that in both theorems one satisfy the assumption of this theorem, but this is something one should do extra. So suppose you have a manifold, so a smooth connected manifold, and suppose we fix number m, and we have vector fields x1, xm. These are vector fields on the manifold. But moreover, these vector fields depend on a parameter. Let's call it lambda. So depending smoothly on a parameter lambda, and let's take lambda 0, 1. So what we want to understand is that the parameter is these vector fields are continuous in the parameter, and at lambda equal to 0 we have some situation, some polarization given by these vector fields, and we want to see this situation as lambda equal to 0 as the limit when lambda goes to 0. Okay, so in other words, so let delta the subbundle, again depending on lambda, defined as at the fiber at the point P is the span of the vector field x1 at P xm lambda at P. Okay? So for any fixed lambda, we have a polarization, we have a subbundle, we have a subset of the tangent bundle. For now, it's just a subset. Okay, but we're going to assume that lambda 0 is, for lambda equal to 0, delta 0 is bracket generating. So this assumption will actually imply that also delta lambda is bracket generating, at least on compact sets, for lambda small enough. Okay? Okay, in other words, for every compact set, there is, if lambda is small enough, then delta lambda is also bracket generating. Okay? So these are the distribution we want to consider. And now let's suppose we also have some norms, again, depending on the parameter, from Tm to R. These are continuously varying norms depending smoothly on the parameter lambda in 0, 1. Okay, so also the norms might change. Okay, so from the choice, of the distribution and the norm, we have Carnot-Carathéodory structure, and therefore a distance. Okay, so let d lambda be the Carnot-Carathéodory distance function associated to delta lambda and the norm, depending on lambda. Okay? Then the theorem states the following. As lambda goes to 0, d lambda converges uniformly on compact sets to the distance d0. Okay, so in brief, what I'm saying is that if you have distribution converging to a distribution, if you have norms converging to a norm, then the distances converge to the distance. This is in brief. Okay, so where this convergence is uniformly on compact sets, and here everything should be continuous in the parameter. Okay, and this convergence is meant as a convergence with respect to the frame of vector fields. All right, so let's take for granted this theorem. We will later go back and give some motivation why this is true, but I want to tell you why from this theorem one can do some extra work and prove various things like Pansu's theorem, Mitchell's theorem. But maybe I will start with the easier consequence that says that every subRiemannian structure is the limit of Riemannian structures. It's something simple, but it's still good to realize. So, consequences of this last theorem. Okay, so the first one, I want to explain that every subRiemannian distance function is the actually we can even have a monotone limit, like an increasing limit. Increasing limit is the increasing limit of Riemannian distance functions on the same manifold. Okay, of course the same analog is also true for Finsler. So if you have a sub-Finsler distance function, that you can see it as an increasing limit of Finsler distance functions. Okay, so let me rephrase it a little bit better. So suppose you have m delta and a scalar product. So this is a sub-Riemannian manifold. Then what we could do, so first of all, this scalar product, let's think it's really extended to a scalar product on M. So we may extend the scalar product to the whole tangent space. We may consider the orthogonal to the subbundle. This is just defined in each fiber, okay? So this just means delta, this is just the delta P orthogonal inside TPM. Okay, so now what we do, we consider a family of norms. So we may consider the scalar product let's call it scalar product with index epsilon, such that, so the two spaces, this is point y, in each leaf, this is orthogonal to this, delta is orthogonal to delta perp, and on delta, the scalar product, it's the same scalar product that we started with, and on delta epsilon is epsilon times the scalar product. Okay? Then what we have is that the Riemannian distances associated to this scalar product converges to the subRiemannian. So the way I stated this result doesn't look like a consequence of the previous one, because now we just have norms or scalar products that converge to scalar products, but we don't have any frame at the moment. Okay, but this is what at least I want to say. I want to say that okay, so the statement is that these distances converge to these other distances. Now, and also look that it is increasing, because you see, every time I choose this scalar product, right, the smaller is epsilon, then the longer is the length of any vector, or at least does not get shorter. Therefore, these distances are getting bigger and bigger. Or epsilon is smaller, then the distance is greater or equal. Okay. Right. Let's try to understand why this can be seen as a consequence of the previous theorem. And so, what I want to say is that, so from this statement, how one can choose frames, right? Because the statement, the theorem before was about frames converging. Okay. So first of all, how do you find a single frame? So what you could do is the following. You have a differentiable manifold, so think of a Riemannian manifold. What you can think is you can apply Nash theorem, or actually even in the Whitney version is good enough. So and you can see M inside Rm. So if you use Nash, you have an isometric embedding. Otherwise, you just need a smooth embedding. So this is good enough. So suppose that M is a submanifold or Rm for some big N. Okay, this is what Nash and Whitney tell you. Now, what you do, you take inside R to the N, take the standard frame. The frame delta 1, delta N on Rn. And now what you do, so suppose you have the manifold, and then in the manifold, at this point, you have this frame, the 1, the 2, the 3, and what you do, you just take the tangent of the manifold, and you just project every vector on the tangent. So you defined x1, xn vector fields on M to be just the projection, so the ith vector at P is equal to the projection on delta P of the ith vector, okay? It's not important that this frame might not be a frame anymore, because I mean, some might even be zero, or they might be linearly, not linearly independent anymore, but this is not a problem. They will still define the correct distribution, okay? Actually, you can also project the frame on the orthogonal. So likewise, yi at P is the projection on delta perp of the I. And these vectors, it's like this, they span at each point delta perp. Likewise, the previous one here, they were spanning at every point delta P. Okay, so now what you consider is the frame. You take x1 up to xn, sorry, capital N, and epsilon y1, epsilon y n. They form a frame for the Riemannian structure depending on epsilon, and they converge to the frame exactly. They will converge to 0, and they will converge to a frame for the horizontal structure. Okay. Okay. Now let's see another consequence. The second consequence that I want to discuss is Pansu's theorem. So the setting is the following. Let n be an nilpotent Lie group and let's equip it with some Riemannian structure. Of course, we mean Riemannian left invariant structure. Okay, so let's say that we denote by n the Lie algebra of this group, and let's say that we have step n, step the group of the let's say a connected, okay, connected important Lie group. Step n, step of n is s. Okay, so now what we do, we let's make it simply connected. This is better, so then we can consider the exponential coordinates. Simply connected. Okay, so now what we do, we choose, as in when we construct the Malchev basis, we choose spaces such that n, so V1 is in direct sum with the derived subalgebra, and in general Nj is Vj direct sum with Nj plus 1, where Nj is the jth element of the descending central series. Okay, so this is by definition is Nj minus 1 n. Okay. Okay, actually it's better if instead of taking the so we have a lot of freedom in the choice of this Vj, but let's say that at least V1 we prefer to choose V1 to be the orthogonal of the derived subalgebra. Okay, so we don't choose it in this way, we choose like this, and from from 2 on, we choose it this way. For all j from 2 to s. Okay. Now we have decomposed the space in this as this direct sum. Okay, so the direct sum of V1 Vs gives the whole algebra N. And now we define some dilation. So define the linear maps. Let's call them delta lambda from N to N. The only maps that are linear and for which delta lambda on Vi is equal to lambda to the I, the identity on Vi. So on Vi multiplies by lambda to Vi. Okay. Some warning. So this might look like the dilations on Carnot groups, but the group may not be a Carnot group. Okay. So some warnings. Unless we are in the presence of a stratifiable group, and Vi is a stratification, then delta lambda are not Lie algebra homomorphisms. And actually, even if the algebra is stratifiable, we might end up choosing some Vj that are not a stratification. You see, here we have complete freedom on any j. So if the algebra is stratifiable and you don't choose a stratification, then the delta lambda are not Lie algebra homomorphism. Okay. All right. In the limit, now we are going to consider some limit. Then at the limit, they're going to be Lie algebra homomorphism. Okay. So let's continue the construction. So now let's pick an orthonormal left invariant frame, say gamma x1 xm of V1, and extend it to an, again, orthonormal left invariant frame x1 xn of the Lie algebra N. Then, now that we fixed a basis of the Lie algebra, we are going to consider exponential coordinates. So, consider exponential coordinates. And we define xi depending on lambda to be 1 over lambda delta lambda star of xi. Now, let's pay attention, okay? So, these are now vector fields seen in the Lie algebra, right? Because we are in exponential coordinates. We have this is a linear map. But let's pay attention, this map is not a Lie algebra homomorphism on the group, it's not a group homomorphism, okay? So this should not be thought as the Lie algebra homomorphism associated with this map. This is just the differential, okay? So this here, this is the differential of the map in exponential coordinates. Okay, so again, so what we have done, you should think of this as taking this orthonormal frame, changing coordinates. Right? So see this map delta lambda as a change of coordinates in Rn. But then what we do, we multiply by 1 over lambda. So you should understand this as we have rescaled the distance by this fact. Right? Now these are not these vectors, that were before orthonormal. Now we declare these vectors to be orthonormal, which means that we have dilated the distance by this factor depending on lambda. Okay. So what one should observe, okay, so there's facts. We mentioned some of them, but maybe not all. So for all I, from 1 to m were the basis of V1, up to m, what happens is that these vectors I lambda, they converge to some vectors. Let's call it lambda 0, as lambda goes to 0. Instead, for the other, from m plus 1 up to n, xi lambda converge to 0 as lambda goes to 0. So you should understand this as this Riemannian structure will convert to a sub-Riemannian structure. They are not going to be a basis anymore in the limit. And really, so what one has to prove is that these limiting vectors, this one x n m 0, these are a frame of the limits of V1 of the first layer of the first stratum of a stratification. Let me stress that these vector fields x1 0, xm0 are left invariant and form a stratification for a group structure and the algebra structure possibly different than the original one. So if you prove these three facts, then what you have proved is that the rescaling the distance, and now you see what we are doing, we are contracting the distance when lambda goes to 0, the asymptotic cone of the Riemannian structure for which these vectors are orthonormal will converge to the sub-Riemannian structure for which these are the orthonormal frame. And this orthonormal frame induces a stratification. So proving these three facts together with the theorem we mentioned at the beginning of the video will prove that the asymptotic cone of this nilpotent group is a Carnot group. Okay, let me mention a little bit more some facts about these three results. Okay, so now let's note what happens if V1 was already the first stratum. Okay, so if V1 is the first stratum of a stratification for n, then, so what you see is that we are dilating by, so this map is really a dilation by lambda, we are dividing by lambda, so it's just stay the same, okay? Then what we have is that xi lambda is equal to xi, the initial one, for all I from 1 to m. Okay, so nothing has changed. Otherwise, what's happening is the following. So if V1 is not the first stratum, what we're going to do is that the group law on n will change, and the vectors xi0 are going to be left invariant vector fields for this new law. Okay. So the group will really change the group structure. Let me describe how it changes. So it's easier to start with the Lie algebra structure, the new Lie bracket. on the same vectors on the vector space. So we're starting with the algebra n, and we will change the bracket. Okay. So suppose you have two vectors of n. Now you want to express the new bracket. So what you do is the following: you take x and y, you dilate by delta lambda minus 1, delta lambda minus 1, so it's two vectors. Then you take the bracket, and then you rescale again by delta lambda. When you take the limit lambda goes to 0, this by definition is going to be the limiting vector, Lie bracket. So what we are doing is we are taking 2 points, we are dilating. Let's think that lambda is very small. So these 2 points will go towards infinity. Then we take the Lie bracket among them, and then we bring them back near to where they were. Okay. So this limit exists and is going to define a new Lie bracket. Okay. Now, let me try to explain why this limit exists. Okay. It's definitely something that is linear, because all these maps are linear. Okay. So let me just show you what happens if you take one vector in Vi. So if x in Vi and y is in Vj, then what happens is the following. So what happens if we take the original bracket, okay? Now, this is going to be, so if you have Vi, so Vi is a subset of Ni, the element of this descending central series, and Vj is in Nj. So we have that Ni bracket Nj is always a subset of Ni plus j. And therefore, what we can do, we can decompose x bracket y as a vector xi plus j in Vi plus j plus other vectors zi plus j plus 1 in Vi plus j plus 1, and continue up to Vs. Zs. Okay, so this is the decomposition. Okay, now what happens when we consider delta lambda of delta minus 1 x, delta minus 1 y? Okay, so this is delta lambda. So since x is in Vi, delta lambda multiplied by, so we have, sorry, right. So this is delta 1 over lambda, which applied to x becomes 1 over lambda to the I x. So which means I write it minus I x delta minus j y. Okay, so now this is, so we can bring it out. So this is delta minus I minus j of delta lambda of this vector here, which is going to be delta I plus j of zi plus j plus delta I plus j plus 1 of zi plus j plus 1 plus delta s of zs. Okay, so now what we have is that the first element here, so these two things cancel, so we're going to have zi plus j plus something that goes to 0, so it's a big O of lambda as lambda goes to 0, and therefore the limit is going to be zi plus j. So the new vector field, the new Lie bracket delta xy at 0, what it does, it really takes the decomposition of the vector and it isolates the lower term. Okay. Actually, with this calculation, it's easy to check that this this newly bracket is a stratification. Now, this was regarding the Lie bracket. One can have a similar formula for the product. Likewise, the product, the limiting product is x product y, defined as the limit of lambda going to 0 of delta lambda minus 1 x product with delta lambda minus 1 y. Okay. So this group law and bracket structure are the ones considered up to change of coordinates via delta lambda. Okay, I'll explain again. What we are doing is the following. We have our space. We have our space N on which we have a group and a group structure or Lie algebra. We have both when we are in exponential coordinates. And now let's see, like if we have two copies of N, and actually it's like if you have a copy on N of N for every lambda, and for every lambda we have this map delta lambda. This delta lambda can be is a linear map. Is a linear isomorphism. Okay? Let's consider it as a change of coordinates. So what we do is we take 2 points here, we bring them back, we bring on N, we perform either the Lie bracket or the group structure, and then of the result point, we bring it back to N. So what we are doing is like, on N, we have a manifold structure, right? And we are considering the map from this other copy of N into N as a parametrization, okay? So what we are considering a sequence of parametrization. But now what we are doing in N, we also have a subRiemannian structure, okay? Or maybe we should consider we have a sequence of subRiemannian structure. There are those for which we multiply by lambda an orthonormal frame. And therefore, what we do now, we bring back this structure, this geometric structure now on N. And what we will see that on N, these structures will converge. So remember that what we defined was xi lambda to be the limit of, see, you bring these maps, these vectors on the new domain of parametrization, but when we multiply by delta lambda, of course we can also write it, so delta lambda star, this is a linear map, so it's like we divide this, so this is going to be a big number, right? So we are considering an asymptotic cone, and then we bring them back in coordinates. Right? This is lambda going to 0. So this, if we prove that these limits of vector space converge, then we have that in these coordinates, the geometric structures, the subRiemannian structures, are converging. And what we have, so first of all, let's clarify that these vectors, at least at 0, they don't blow up, they don't go to 0. So at 0, we have, so 1 over lambda, delta lambda xi at 0. So this vector is a vector in V1. This is really exactly as xi. So this vector gets multiplied by lambda and then divided by lambda. So this is for all lambda and for all I greater than 0, for all I from 1 to m. Okay, so what happens? The vectors x1 lambda and xm lambda stay a frame. They are also a frame. Also, as lambda is equal to 0. Actually, it's easy to verify that these are left invariant with respect to the new group structures. So they are these vectors x1 lambda up to xm lambda are left invariant with respect to the new structures. Namely the structure of the product at time lambda, but also at time 0, and the Lie bracket at time lambda and at time 0. So they are left invariant, and at lambda equals 0, they form a frame for a stratification. So, and the stratification is V1 with respect to the product 0 is going to be V2, and Vi V1 with respect to the limiting scalar product, Lie bracket is Vi plus 1. And again, because what I said before is that because we multiply the frame, the orthonormal frame, by 1 over lambda, with lambda going to 0, we are taking the asymptotic cone, or the asymptotic cone. Okay, what is the conclusion of all this discussion? The conclusion is that for all n rho is a Riemannian structure, is a nilpotent Riemannian Lie group, where rho is a left invariant Riemannian structure, and therefore we consider the Riemannian associated distance, then n rho has an asymptotic cone that is a Carnot group. And this is known as Pansu's theorem. If you liked the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.